Hello, my name is Andreas. I will be presenting our paper Distractor-Aware Video Object Segmentation. For those that are not familiar with this topic, video object segmentation attempts to track one or multiple objects and paint the pixels on them. Specifically, we're given a starting video frame and a mask covering a target of interest. Together, these are used to define what the video object segmentation method is supposed to attend to. When new frames are provided, the method should paint the mask in new frames. There can also be multiple segmentation targets in the same video. The typical way to deal with this situation is to run multiple segmenters in parallel. Each one trains and maintains its own so-called target model. A target model can only recognize its own target and considers the others as part of the background. It's also trained and tuned continuously while the segmenter is running to adapt to changes in the target's appearance. And this is, of course, in contrast to neural networks that are trained in advance. Up until this point, the segmenters are operating separately, but in the last step of the processing of a video frame, their target masks are combined into a so-called label map. The most common is to regard it as a classification problem and select the most likely object on a per pixel basis. But there is a problem here. If you pick any target, there could be other objects that are more similar to that than the background. So we require that the target model should not only tell the target and the background apart, but also deal with objects in the background that are similar to the target. So the solution that we apply in our work is to split the background class into a new background and a new distractor class, and can collect objects similar to the target in the latter. The split should make the segmentation more accurate. However, to do this, you actually have to find the distractor somehow. To keep things simple, we chose to simply combine all the other annotated objects. Another possibility is to have some self-supervised method detect and rank problematic regions in the background, but that's for another project. So far, I've only talked about video segmentation in general terms, but we need to zoom in on a particular method, see how it works, and then modify it. We base our work on a recent method called learning what to learn, which operates as follows. At the start, we provide the first image and extract deep features from it with this resonant backbone. We also input the target mask or label and encode it into an embedding of the same resolution as the deep features, in this case 1/16 of the image size. Both pieces of information are added to a memory. The samples we store here is the training data for learning the weights of a discriminative correlation filter, and this is our target model. Once the target model is trained, we extract image features from the next image and pass them through the filter, which is F here. Since the filter is trained with encoded labels, it should also produce encoded labels, now representing the mask of the target in its new location. To recover the mask, we give the encoded labels to a decoder and upsampler network. It progressively refines the embeddings to up to 1/4 resolution, guided by deep image features from the backbone. It is then upsampled to full resolution in a final stage. Finally, we add the new mask and the corresponding image features to the memory so that the target model can be trained some more and adapt to visual changes. Adapting this structure for our purposes is straightforward. We want to maintain a second target, the distractor, and we construct it from the masks of other targets. Formally, we can say that the distractor of target I is the union of the binary masks of all the other targets j. So here di and 1di denotes the distractor and its mask associated with target I, and tj and 1tj are the targets j and their masks. Another way to express this is in terms of the label map L, or the image of all the segments, numbered by their target ID. Each pixel in a segmentation mask is associated with the estimated probability of that pixel belonging to the target. When designing our distractor, we could simply input binary values to train our model, but from previous experience, we know that it's better to use the probabilities. Now we want to merge probabilities from multiple targets. In each pixel, we let the most confident target classification set the confidence for the distractor. This is done with a Pmax function. PTJ is the per pixel probability of target J. Similarly, we get the most confident background probabilities with Pmin function. We then combine the two like this, using the distractor mask in the first term and the, let's call it not background mask in the second term. We name this the winner-takes-all function, in that the most certain predictions from each target win in every point. Going back to the baseline, we start with this structure and insert the winner-takes-all function. concatenating its output with the target masks. The predicted distractor in the lower right corner here is an artifact of the training. It's not propagated forward to the next frame since we use the winner-takes-all function's value instead. However, it should be helpful to the decoder when it reconstructs the target. This is the core idea and simple to implement, but it doesn't actually work by itself, and we had to make some additional changes. Our hypothesis is that to benefit from distractors on the datasets that we have, you must also reduce ambiguity and manage uncertainty near object boundaries. We do this by increasing the resolution of the deep features we train the target model on. We also replace the decoder's rather naive upsampler with one that is context-aware. Specifically, we adopt the upsampler from the Raft optical flow method, but of course apply it to RGB instead. So let's have a look at the experiments we did to understand the contributions of each addition. I'd like to preface this by saying that it would have been nice to see that adding one feature at a time gradually improved the scores, but that's not the case here. We test on Davis 2017, the validation and the test dev splits. The headings on the left denote the additions we made. L2 is adding block 2 features into the model training data and doubling its resolution. D is for the distractors, and U, the context-aware upsampler. B stands for balanced training loss, which I'll get back to in a bit. These are our baseline results. The numbers represent the mean of the intersection of a union and F-score, which are the metrics used to judge video object segmentation methods. These are the results with the distractor. As you can see, not much happens. Here we have the upsampler. Still no improvements on the validation split, but the results in the test dev are encouraging. We then looked at doubling the resolution of the features that we trained the target model on. As you can see, they provided enormous benefits by themselves, but adding the upsampler makes it worse. But here we see that only when we combine all three components is there a fairly large improvement on both dataset splits. Here we move to test on YouTube VOS, and that did not turn out so well. Curiously, none of the things that worked on Davis have any effect here. Now we started thinking about how the datasets are different, at least qualitatively. One hypothesis is that distractor objects will cover a much larger image area than the target, as they are composed of multiple objects and take up more pixels. This will skew the loss during training towards generating perfect distractor outputs from the decoder at the expense of the actual target. So we introduced loss balancing to proportionally reduce the influence of the distractors should they cover more pixels than the target. And here we can see that it helped on YouTube VOS and a little bit on Davis test dev, but not for Davis validation. Why we get these wildly different changes is unclear. Let's compare the results with the state of the art. Despite the, shall we say, divergent results, are we on par with the single scale variant of CFBI in the top row? The multiple scale variant on the line below is much better, but not directly comparable. The 77.5% was achieved by increasing the video resolution from 480 to 600 pixels. We could have done that too, but then we would not be comparable with any of the other methods. So it's perhaps best to put this in parentheses. The main takeaway, at least, is that we show good improvements over our baseline with something new. Now let's move back to the ablation study a bit, because we tested some additional aspects of the distractors. It's the three results between the horizontal bars that we should look at now. They're listed above the balanced loss experiments since they were performed before it. In the no distractors variant in the middle, we simply replace the winner-take-all with 0 during segmentation, still with a decoder that was trained with distractors, and the results drop back to baseline levels. This should confirm that the distractors themselves are helpful. In the no WTA variant, we skip the winner-take-all function and instead feed back the distractors generated by the decoder into the target model. As you can see, test dev drops back quite a bit, which shows that the function is actually useful too. Now, I think the most interesting of the three is the hard loss experiment, which will need some more explanation. While training, we use the Lovász softmax loss. This is a differentiable surrogate for the intersection of union metric. This loss is applied jointly to targets and distractors. But the distractors are effectively auxiliary information, and since we're throwing away those produced by the decoder in favor of the winner-take-all function, we can relax the network training loss. In sequences with only one target, and hence no distractors, as we define them here at least, we allow the decoder to place distractor segments anywhere except on the target, and call that the relaxed loss. Normally, one would enforce that no distractors should be output at all when none are given as input, and we name that the hard loss. Going back to the ablation, we see that the relaxed loss is necessary because the results drop by 3.5 points to 80.2 on Davis validation. At the same time, which is somewhat of a theme in this paper, test dev improves to 74.9. So what qualitative difference can these two losses make? Here we see the camel sequence from the Davis validation set. On the left is the input video. In the middle are the class log likelihoods from a decoder trained with a relaxed loss, and on the right are those from a decoder trained with a hard loss. The target class is in the top row and the distractor in the bottom. In both cases, the color scale is the same. Red and yellow are positive, blue and cyan are negative, and yellow and cyan implies higher amplitude than where we see red and blue. Log likelihoods near zero are black. There are two things to see here. One is that the hard loss variant is much more confident than the relaxed loss. The other is an interesting phenomenon resulting from the relaxed loss. Here the decoder decides for itself that the camel in the background is a distractor, if only for a moment. You can see that the effect is still there in the hard loss, but it's much less noticeable. This is one of the things that probably should be investigated more. Finally, let's have a look at another qualitative but more practical difference that distractors can make. Here we have a video with people skiing past the camera. The middle row shows the baseline and the bottom row our result. Every time a new skier comes in, a target model is trained on it and segmentation begins. This works well until the skier assigned to the blue mask appears. We can see that the mask in the middle row, made without distractor modeling, quickly deteriorates, but the one with distractor modeling below it does not. The last skier is not annotated, and both methods freely assign it to a target, since it's similar to the other skiers. Anyway, it seems that the better model makes it easier to distinguish between the targets, like we'd hoped. So let me summarize. We've extended a video object segmentation method to consider possibly similar and distracting targets. At the same time, we found it necessary to reduce the ambiguity and manage uncertainty by increasing the feature map resolution and incorporating a context-aware upsampler. And the results are mixed. A component that improves the results on one dataset can at the same time be detrimental on another. It's unclear what could be the cause of this, but it is perhaps an indicator that we need more data. Finally, in future work, a self-supervised method to detect the distractors could be developed. The example with relaxed versus hard losses suggests there's a tendency in that direction already. That's the end of this talk. Thank you for listening.